Hello and welcome. In this video, we'll go over how to configure the Upsert Sub-Workflow. If you've come from the scraper video, you likely already have the manager set up and configured to use the Upsert Sub-Workflow. Our objective now is to take that scraped data from the previous section and put it into a vector database, which in this case is a Pinecone index. Let's open it up and take a closer look. Essentially, what's happening with this workflow is we'll take the scraped data from Google Drive, extract the text data, and split it into smaller pieces. Those smaller pieces, called chunks, are then converted into a numerical representation of the text called embeddings. The embeddings are then paired with relevant metadata and added to the Pinecone index. We should already have a Pinecone account from the Getting Started video, and we'll create an index in just a moment. First, though, I want to talk about some of the parameters we can tune in the Set Inputs node that directly relate to the index. In this example, I've gone with a somewhat larger than typical chunk size and overlap, and a somewhat smaller vector dimension size. This is mainly to save on storage. Pinecone's free tier includes 2 gigs of storage, and while that might not sound like much, it's more than enough to store multiple websites, especially at these specifications. For example, my project index contains about 4,200 sites and documents, and it's only just starting to approach a quarter gig, so there's plenty of wiggle room to work with here. Let's go into a bit more detail on these. The chunk size is how many characters are in each data chunk, and overlap is how much of the previous chunk's data is present in the next. Having that overlap keeps relevant data together. For example, if there's a large document that's been broken into many chunks, if relevant data from one chunk is present in the next, we're more likely to pull it during the retrieval process. Our AI agent will be able to piece this information together from the given context and answer user questions more effectively. Vector dimensions are the length of the array used to represent a chunk of text in the embedding space, which is dictated by the embedding model we choose. For example, I've selected this Llama embedding model, which allows for a dimension size of 384 all the way up to 2048. In this example, I've gone with a dimension size of 768 as a common dimension and a good midpoint for this particular model. A larger vector dimension may capture a more nuanced representation of the data. However, that comes with the increased cost of storage and compute. Plus, depending on the quality of your data, it may not make much of a difference. I'll talk more about how to further improve your system in the agents video, which includes modifying the chunk size and vector dimensions with considerations for space and compute. Essentially, though, decreasing the chunk size or increasing the vector dimensions would increase the space required, which isn't necessarily a bad thing, but I recommend additional filtering and re-ranking options to optimize your results first. Regardless, at this dimension and chunk size, we'll still be able to pull some really good results and answer user queries effectively, so we'll just leave everything set as default. Finally, I've set one of Pinecone's sparse embedding models to use in this example. Unlike dense models, sparse models do not have a fixed length that we need to worry about, so I'm just going to leave this as default and go into more details about the differences between dense and sparse in a little bit. Now that we've touched on all the parameters, let's create our Pinecone index. Navigate to pinecone.io and create an index. Name the index what you like. I'll just go with the account name for now. And since we're using both dense and sparse vectors within a single index, I'll need to select the Custom Settings checkbox. We'll keep the vector type as dense and enter 768 for our dimensions. Finally, change the metric to .product and create. This will create a combined dense and sparse score for our chunks, which guides what chunks are brought in during retrieval. We can now copy this host name generated and add it to our Set Inputs node. Since our example is Ready.gov, I'll change the namespace from demo to ready-today's date. I'll also add a C at the end to denote that this namespace was constructed with a full crawl of Ready.gov in comparison to running the update workflow and just getting the most recent pages. Those namespaces I usually mark with a D for differences, and of course I'll touch on that in the update video. However, feel free to name the namespaces whatever you wish. Which should complete our setup for the Upsert Sub-Workflow. However, I'll just double check that the Pinecone nodes have the credentials linked. And we're ready to kick off the first run. Let's go back to the manager. I'll delete the loop so the system runs just one time, then kick it off. Once done, I'll return to the Pinecone index and see what we've collected. As you can see, we have some data in here now. And our namespace has been created. I'll fetch a single entry from the namespace and explain what we've captured. These values represent the dense numerical representation of this chunk of text. When a user asks a question in the system, that query is converted into a numerical representation too. If the two numerical representations are semantically close enough, then this item would likely be pulled during the retrieval process as context to help answer the user's question. A dense search finds information based on the meaning of the question, even if the exact words used in the documents are different. However, since this is a hybrid index, we have another set of values to help the retrieval process called sparse values. Sparse search finds the information by matching specific words or phrases together that appear in both the query and the stored documents. Hybrid search combines the dense and sparse search so the system can understand the meaning of the question while also matching important keywords. Along with these values, we've also captured some useful metadata, including the chunk order, so when a document is broken into text, we can tell if this was at the top of the page, as in chunk 0, or further down, 2, 3, 4. As you can see, the actual text of the chunk has been captured as well. Then the file name metadata is important for maintaining the namespace long term. We'll learn more about that in the Update Sub-Workflow video. Essentially, I have tools that look for this attribute and then can use that to clean up the old data before bringing new data in. That way you don't always have to do a full crawl when updating the namespace with new data. Last modified is now an optional metadata, as not all websites actually have a last modified value. If yours does, though, you could update the AI agent prompt in the agent video to give this data along with the source metadata URL as well. That way your users know where the information came from and how old it is. What is included, though, is the source metadata, which, as I said, whenever the AI agent answers the user's question, it will give a list of source URLs based on the items it pulled in, so this metadata entry is needed for that output. Now that you see what data is being collected, let's finish upserting the rest of the data into this index. I'll go back to the manager, relink the loop, then kick off things once more. So this before an hour hit, I actually hit an error here, and it's one of the more common ones, so I figured I would share it with you. Running one item at a time through this system, we should be well below the Google Sheets current rate limits. However, because this is a free tier account without a credit card linked, Google services can automatically deny requests just based on global traffic demand. So you can finish the job like I'm doing here by moving the item to the process sheet. Restarting the job as is may result in some duplicate data, but usually doesn't throw things off too much. One of the better strategies is simply to run these bigger jobs at night. As your project grows, it'll make sense to move away from Google Sheets and instead look to a database platform like Supabase, for example. In the update and sitemap video, I'll go into a full example on how to use Supabase, so keep that in the back of your mind if you start seeing this error more often. We now have everything loaded into our vector database, and we're nearly ready to start asking some questions of our data. Let's configure the sub-workflow which retrieves the results from the index called query_kb. Here on the set inputs node, we'll set the Pinecone host. I'll grab that host name from Pinecone real quick and confirm our dimensions. I'll paste the host name and enter the name of our namespace. The dimensions are 768, so I'll leave this as is for now. Finally, top K is a setting you're most likely to play with in this workflow. Top K dictates how many items are brought in during the retrieval process. A smaller top K may not give enough information to answer the question, while a large top K takes longer to process and costs more tokens. 20 has been a good number in my testing, so I'll leave that as is too. We'll double check the Pinecone nodes to ensure the credentials are loaded, then we'll be good to go. Let's open one of the agent workflows. Head on over to the main workflows page and open up the Gemini flashlight agent. Now we'll set the query_kb workflow we just configured as the sub-workflow to be called. Then double check that our credentials are recognized in the Gemini API model. I'll go into a lot more detail about this entire workflow in the next video, but for now, let's just ask the question about some of the data we've collected from Ready.gov. Ready.gov contains a lot of information about various kits you can make to keep you and your family prepared in the event of an emergency. However, something I really want to know is if I just need to keep a bag of 10 items in easy reach, what would those be? Now, some of these items make a lot of sense, but one that catches me by surprise is the whistle. I don't think I would have ever considered that in an emergency kit, but that's actually a good idea. As you can see in our output, we have a list of sources used to answer this question, which we can throw into the search bar to make sure it's an actual URL. I'm also going to turn on an optional feature, which will ensure that the source list is always outputted as a bulleted list. You can, of course, modify the system message to give an example of the preferred output, but this method is reliable and serves as a good example on how to modify the agent output before it makes its way to the user. Let's do one more quick example. Let's say I work for Ready.gov and I need to find and print this document. It's not a common enough document that I have bookmarked, but I know it has the words emergency supply list. If I refresh and run a new query with just that, it will likely give me the URL I need to just look it up real quick. This is really useful when searching through a lot of documentation. If you can only remember a few specific words for a document, there's a good chance the agent can find it faster than you searching for it yourself. And there we have it. We've gone from crawling a list of URLs to scraping the pages of documents, uploading those documents into a database, and asking it some questions using our AI agent. There's still plenty more to go into, but we can finally see the fruits of our labor. In the next video, I'll go deeper into this agent setup, including the models used and other examples beyond Ready.gov. Thanks for watching.